This is the second of two videos introducing nonlinear finite element analysis. In this video, we'll go through several examples showing how the Newton-Raphson and modified Newton-Raphson approaches work on real systems. Here's a quick flowchart indicating what happens in the Newton-Raphson method as well as the modified Newton-Raphson method. I went through this in some detail at the end of the prior video, so in this one all I'm going to do is highlight the steps that we go through during each load iteration, and I'm going to label them so that you'll see them as we go through the later steps. So first off, you need to calculate a tangent stiffness, then you find the new displacement, then you find a secant stiffness, you find the load predicted by the structure, the reaction load of the structure, and then you find the load error, the difference between the applied load and the reaction load. So I think this process is best understood by walking through an example. Here's the Newton-Raphson method applied to a force displacement curve that we see shown dotted here. This dotted curve, remember, we don't actually know it if we're running FEA. What we know is we have the ability to evaluate the displacement under some given load, and that's what we're going to do. So our goal is to find the displacement at load P, and we're going to break it into two increments. Just to show you the process, I want to have just two increments here. The first load increment corresponds to a J of 1. And we start that increment by finding some initial conditions. So for load increment 1, what is our initial displacement? Well, it's 0. What is our initial reaction? That's also 0. And what is our load error? Well, it's the difference between the 0 reaction load and the expected applied load of P1. So in other words, it's just P1. So for iteration 1, in other words, we have I equal to 1. So remember, I is our incrementation variable. The first step, A, was calculating a tangent stiffness. That is the immediate slope right at U equals 0. And we do the calculation for that. Then we evaluate what our displacement is based on that initial tangent stiffness. In other words, we take the load error and we divide it by the tangent stiffness and we add it to the original displacement, which in this case was 0. C then is we calculate a secant stiffness, which means that we simply evaluate the stiffness of the curve at the location U1, and it ends up being the green line shown there. D, we evaluate the structure reaction force, R1, that's simply K1 times U1. And then the load error is the difference between where we want to be, P1, and R1, where we were initially. Okay, so then we go on to iteration 2, still in load increment 1. We don't need to do the initial stuff. We now just can jump right into A through D. So calculate a new tangent stiffness, evaluating everything at U1, and then a displacement estimate building off of the U1. We get now a U2. Then a secant stiffness corresponding to U2. Then a structure reaction force, which is K2 times U2. And we can get our new load error, which is P1 minus R2. We need another iteration here because we aren't small enough yet. So this is now iteration 3 for load increment 1. We calculate a new tangent stiffness, again at the location of U2. Then we get a new displacement estimate, U3, based on that tangent stiffness. We get a new secant stiffness, and then we evaluate the structure reaction force by multiplying the secant stiffness times the displacement estimate U3. We get our load error, which in this case is pretty darn small, and we are done with load increment 1. So then we go on to our second load increment. So this is load increment 2, or J equals 2. And our final information from our prior estimate, we need that still. So we need K final, R final, and U final. That's why I've left them on here. So we now in a new increment, so we need to find those initial conditions. Our initial displacement is equal to the displacement in our final step, our final iteration step from our first increment. Similarly, our reaction is our final force reaction from our first increment, And then finally our load error has now increased to be the P2, which is our final load in this case, minus R0, our current reaction. Okay, now let's start iteration 1 within this second load increment. Again, we start out by having a tangent stiffness, which is the slope of the curve at that point. And then from that we can calculate a displacement estimate. And that's going to be a U1. This is now a new U. We start I over again for each increment, load increment. We calculate a secant stiffness corresponding to U1. Then we get a structure reaction force. And finally we get a load error. In this case, our load error is going to be a negative number because we overshot. That's okay. The nice thing is this is a self-correcting iteration process. So now we can move on to iteration 2. For iteration 2, we need, again, a new tangent stiffness and then a displacement estimate based on that tangent stiffness. Then a new secant stiffness, K2, a new structure reaction force, R2, and a new error, which is E2. You can see we're closing in here. Iteration 3 for load increment 2, a new tangent stiffness, a new displacement estimate, a new secant stiffness, K3, a structure reaction force, R3, and then we find again our load error is approximately 0. So we are done with this analysis. We have converged with 2 load increments to a final value, which is U3. That's the displacement corresponding to our total load P2. Let's pause real quick here and look at how the Newton-Raphson method can be written as a flowchart for multiple degrees of freedom. So again, we break the load into load increments. We start with a load vector corresponding to our current load increment. We then find some initial values, which are the degree of freedom vector at iteration 0 and the reaction force vector at iteration 0. Then we calculate a tangent stiffness by evaluating our secant stiffness at iteration 0 and then taking a partial derivative of our secant stiffness with respect to all of our degrees of freedom. This is obviously going to be a numerical approximation we'll be making in FEA to do that derivative. And then that gets multiplied by our D0, our degree of freedom vector for 0 increment. Then we get a new displacement or degree of freedom vector, D1. We use that to get a new secant stiffness, Ki, or K1 in this case. And then we find a new load and a new load error, so Ri and Ei, all of those being load vectors. Then we ask the question, is the load vector small enough? And here, because it's a vector, we need to find the norm of the vector. If it is not small enough, we iterate, so I increments by 1, so I becomes 2 for this second time through, and we repeat all those steps. If it is good enough, then we go back to our next load increment, so we increase the load. And again, just like with the 1 degree of freedom, modified Newton-Raphson cuts out the calculation of the tangent stiffness. That's a pretty big calculation, so that's a huge time savings in terms of the FEA, but it can be somewhat unstable. Let's take a look at how the modified Newton-Raphson method would get applied on a softening structure. By softening, I mean a structure like the dotted line shown here, where the stiffness gets less as the displacement increases. So assume that we want to apply some load. I've got a horizontal blue line indicating that, and we're going to apply modified Newton-Raphson. Initially it looks the same. We calculate an initial tangent stiffness that gives us an initial estimate of displacement, which gives us a reaction force and an error term. We then evaluate a new tangent stiffness. No, we don't. That would be standard Newton-Raphson. Modified Newton-Raphson is then going to use the same tangent stiffness that we just used and apply it at this displacement U1. which gives us a new displacement estimate U2. Again, a new reaction force and error term. We're going to apply the same tangent stiffness. We get a new displacement term, same tangent stiffness, new displacement term, tangent stiffness, displacement term, tangent stiffness, displacement term, and so on until eventually we converge. You see that we're heading in the right direction, but it's going to take a lot of steps to get there. So why do we bother to do this? Well, fundamentally, it's because recalculating that KT takes a lot of computation time. It turns out that for a lot of systems, you are better off doing lots of shorter iterations, such as this, than doing a much more complicated, fewer set of iterations by recalculating the tangent stiffness. Let's take a look at a quick example of the Newton-Raphson method applied to a hardening system, so one where the stiffness increases as the displacement increases. So assuming I'm applying a load as shown here, I get an initial tangent stiffness, which gives us an initial estimate of displacement, and that gives me my initial reaction, and a negative error comes out of this case. But then I calculate a new tangent stiffness and apply it with that negative error to get a new displacement estimate. So I head back in the direction I need to go. I get a new reaction force, another negative error, a new tangent stiffness term multiplied by that negative error gets me a new displacement estimate. Looks pretty good. There's a tiny bit of error still left in this case. We could do one more iteration, or we can call that good enough. So even on a hardening system like this, where we overshoot initially, it comes back and we'll find the correct displacement for Newton-Raphson. But what happens with modified Newton-Raphson? So again, same curve, same applied load, same initial tangent stiffness, same load increment, but now we have the reaction force and the negative error, and then we apply the same tangent, and then we're in trouble. So now we get into negative displacements. Depending on how well behaved your system is, you might still converge, but a lot of times this is an indication that you are diverging. And in particular, modified Newton-Raphson has problems with hardening systems. So it's probably worth putting in the additional time to do the full Newton-Raphson if you know that your system is going to get stiffer over the analysis as displacement increases. Let's wrap up this video by going through a numerical example with a nonlinear spring. I'm going to use the Newton-Raphson method to find the displacement of this system, U, with a load applied of P equal to 1. We know that P is equal to K times U, so therefore we can calculate the tangent stiffness. It's equal to the derivative of P with respect to U, and I use the chain rule to find that that's equal to K secant stiffness K plus dk du times U, or in this case it becomes that function of U. I combine that together and I get an expression for my tangent stiffness for any iteration UI, for any displacement estimate UI. Now let's go ahead and make some initial decisions and get started. I'm going to break this into two load increments. So my first one, P1 is equal to 0.5, and I'm going to choose my max error of 1%. Starting load increment 1, I have P1 equal to 0.5, and my displacement and reaction force initially are 0, so my error is 0.5 pounds, for example. Iteration 1, start out by calculating a tangent stiffness. I plug in a displacement of 0, and that gives me a tangent stiffness initially of 1. I can then use that tangent stiffness to give me a initial displacement estimate, so U1 will be equal to 0.5. Now I can find K1 by evaluating K at U1 equal to 0.5, and that gives me 0.816 for my initial secant stiffness. And then let's find our reaction force of the structure. R1 is equal to K1 times U1, which comes out to 0.408. Our error is then the difference between my anticipated load of 0.5 and my actual load of 0.408, so it's 0.092. So not good enough. We have to continue our iteration. Iteration 2, I need to get a new tangent stiffness of 0.68, a new displacement estimate of 0.635, a new secant stiffness of 0.782, a new reaction of 0.497, and a new error of 0.0034, which is going to be good enough. That is less than my max allowed, so load increment 1 is complete. Let's go on to load increment 2. So continuing, load increment 2, I'm going to have that go up to my max load now of 1. I've got an initial displacement and load and error, displacement and load that come from the end of my iteration or my increment 1, and then my error is the difference between P2 and R0. So that's the 0.5035. It's important to take the reaction force from the end of the prior rather than where you thought you would be, because otherwise you will build up errors as you go through multiple increments. Okay, for iteration 1, we calculate a tangent stiffness, we get a displacement estimate, then we have a secant stiffness, a reaction force, and an error. We find in this case the error is too big, so we go on to iteration 2, get another tangent stiffness, an updated tangent stiffness, a new displacement estimate, a new stiffness, secant stiffness term, a reaction force, and a new error which is now small enough, and that means our analysis is complete. So visually, this is what we did. We had 2 iterations in increment 1, and we had 2 iterations in increment 2, and you can see this was a pretty well-behaved function, so we really didn't need much more than that in order to make it work out. So that's the basic idea of nonlinear analysis using the Newton-Raphson method, and you can apply that now in FEA.